Okay, now let's move to Nernst equation. Nernst equation is used to calculate the cell potential or electrode potential when there is a change in concentration of the aqueous ions at 25 degrees C or 298 Kelvin. Okay, let's take a look at the formula here. Okay, you have the formula is E equal to E naught cell minus 0.0592 divided by N times log Q. Q is the reaction quotient, and how to find Q is that the concentration of the product divided by concentration of reactants. Okay, XY is the number of moles of product and reactants. Okay, N is referred to the number of moles of electron involved in the redox reaction or the electron transfer in the redox reaction. Okay, when the system is in heterogeneous, so there is involvement of solids, so the concentration of the solids is not included in the Nernst equation. Example here given on how to calculate the cell potential for zinc copper cell when you have the concentration of the product zinc 2 plus equal to 10 molar and the concentration of the reactant copper 2 plus equal to 1 molar at 25 degrees C. So you are given here the half reaction for reduction and half reaction for oxidation, and each of the reactions will have their own E naught cell, which is positive 0.34 volt for reduction, and E naught oxidation is positive 0.76 volt. So how to find the overall reduction? Here we just need to cancel out the electron. Okay, make sure you balance the equation first, and then you cancel out the electrons, and then you write down what's left on the half reaction. Okay, so here you have copper 2 plus zinc producing copper plus zinc 2 plus. So how to calculate the E naught cell for the system? We can have here the equation is E naught cathode minus E naught anode. E naught cathode is the reduction potential, E naught anode is the oxidation potential. But in this case, we need to reverse or change the oxidation to reduction, so you will get a negative 0.76 volt. So you just need to 0.34 minus negative 0.76 volt, you will get positive 1.10 volts. This is the overall E naught cell for the system. However, in Nernst equation, we have to neglect the solid form, so we need to have the concentration of the product in aqueous form and the concentration of the reactant in aqueous form. Okay, so we have here the Nernst equation where E equal to E naught cell minus 0.0592 divided by N times log Q. Q is the reaction quotient. So how to find Q is that we just need to use the concentration of the product divided by the concentration of the reactant, where you have here 10 molar divided by 1 molar. And the N here is referred to number of moles involved in the redox reaction, and E naught cell that you already have is a positive 1.10 volt. So you just need to substitute all the values in the Nernst equation. You will get the new electrode potential is positive 1.07 volt. Let's see the overall reduction here. What happened when we increase the concentration of the products formed and reducing the concentration of the reactants used? So the reaction quotient will be the concentration of the product is higher than the concentration of the reactants, so the Q is increasing. Let's say we have the Q value is 200, so we just need to substitute inside the Nernst equation. So what happened is that you will get the E potential is positive 1.03 volt. What does it mean by this value? Comparing the value from previously, where we have positive 1.70 volt, this one is less than this one. So meaning that when Q is higher, the electrode potential is decreasing.